Hello everyone. I'd like first of all to thank the organizers of this interesting conference and for inviting me today to present our work. I am Mohammed Bourzik. I am PhD student in the Faculty of Sciences and Technology of Fez. My supervisor is Mr. Hilali Ahmed, who is a full professor with Ahmed University of Fez, and Mr. Hilali Abdelmajid, who is a full professor with the Faculty of Sciences and Technology of Fez. Our work is about the dynamic wireless charging of electric vehicles, and exactly we search for the profitable gates location in the highway of the dynamic wireless charging transmitter for the electric vehicles. The order of the presentation is as follows. Firstly, we start with a small introduction containing the general theme of our work, the previous work, and our contribution. Then we'll move into the modeling of the problem, of which we will transform the problem into a mathematical model with continents. In the third paragraph, we will solve the problem with the CPLEX optimizer with limited instances. And finally, we'll finish with a conclusion and perspective. The electric vehicles is composed essentially of the battery system and electric motors, and we can charge them with three charging modes. The first mode is stationary charging, from which the electric vehicle can be charged when it is stopped wirelessly or by the cable. The second mode is quasi-dynamic wireless charging, in which power is transferred when a vehicle is moving slowly or in stop mode. The third mode is the dynamic wireless charging, which allows an electric vehicle to be charged without physical connection and while it is in motion by a set of power transmitters. Each power transmitter is composed of an inverter that supplies a limited length of inductive cable with a direct current, and the inductive cable has the potential to charge dynamically the vehicle's batteries. Among the three modes, we are interested in the dynamic wireless charging because it can charge the vehicle each time while it is in motion, and it is useless to stop each time to charge. For that, there are many works treating the thematic of electric vehicle and the dynamic wireless charger. The principal idea for these works is to search for the optimal location of the electric vehicle infrastructure, which means how we can answer the threat of the vehicle by the minimum of the power transmitter in the road. However, this work is made in the city which characterized by the small and the medium trip. And also, it's assumption that all the vehicles have the same batteries. In this case, all vehicles have the same usage of power transmitter and the same usage costs. For this purpose, in our work, we assume that the electric vehicle infrastructure is predefined, and we made this study in the highway because the electric vehicle batteries drain very quickly due to the high speed and the long distance between the origin and the destination. In addition, we consider a fleet of vehicles with heterogeneous batteries. By this assumption, our problem is as follows. We consider a highway route and the location of the power transmitter is in the second route, represented by a charging lines, and the fleet of heterogeneous vehicles begin the trip from the origin of the route to its destination. Each vehicle type can use the second route to charge its battery. On the other hand, the use of the second route is not free. For that, we assume that at the beginning of each charging line and the end of each charging line we find an entry gate and exit gate. So we can represent the route by the following figure. The route is divided into zones, the first without power transmitter and the second with the power transmitter. The power transmitter in the second zone represents a charging line, and at the beginning and the end we find an entry and exit gates. So if the vehicle needs to charge its battery, it uses the second route. In this case, it must pay the user's charging cost from the entry gate to the end gate. And this is expensive for the vehicle, which saturates its batteries before the exit gate. For this purpose, we search in this work to create a new gates in each charging line to minimize the charging cost of each vehicle type. To achieve our goal, we divide the access route of each charging line into potential gates, and to minimize the charging cost of each vehicle type, we will determine which gates opened and closed. Due to the heterogeneity of batteries vehicle, the number of open increases because each type will use a set of gates to minimize the charging cost. And if the number of the open gates decreases, the charging cost in this case increases. For that, we assume that the charging cost is composite of the charging costs due to the usage of the dynamic wireless charging system and the charging cost due to the usage of the highway gates. The second assumption, the dynamic wireless charging system have a limited life noted by T. In this case, the gates gain is equal to fee service paid by the vehicle in the time T minus its installation costs. We can define in this case two types of gates: no profitable gates, which is have a negative gain, and the profitable gates, which is have a positive gain. So the objective become minimize the charging cost for each vehicle type during their trip on the highway, and the second objective is maximize the profitable gates in the route during the dynamic wireless charging system life noted by T. So to model the problem, we note by O the origin of the route and S is the destination, and each charger line is noted by G. As mentioned previously, we discretized the axis-wood of each charging line into potential gates, and each gate is noted by I, and the last by NG, with NG is the number of the gates in the charging line G. And also we consider the following notation in data, with ZG equal 1 if the charging line G is active and 0 otherwise. For the variables, we consider T alpha G I be the arrival time of the vehicle alpha at the gates I of the charging line G. For the decision variable, we consider xig equal 1 if the AM gate of the line G is open and 0 otherwise. So we model the problem with the following constraints. With the objective is to maximize the profitable gates. So the first term represents the fee service paid by the vehicle. Second represents the installation costs. The second objective is the first term represents the charging due to the use of the charging line, and the second term represents the usage cost of the highway gates. So to solve the problem, we use the CPLEX optimizers, and among the characteristics of this solver, it can solve just a mono-objective problem. For that, we solve our problem for each one of objective. We consider a route with 2000 meters and 4 types of vehicles. The location of charger line is predefined. You consider the following transport network data. The first table is for the charger line status, and the second is about the vehicles data. So we get the following results. For the first objective, when we search to minimize the profitable gates in the route, we get 40 gates in the route, and all gates have a positive gain. We can explain these results by that the full use of the active charging line can answer the trip of each vehicle type without remaining out of charge, and the majority of the vehicles use this gates. For that, the gates have a positive gain. However, when we search to minimize to maximize the profitable gates, the vehicle must pay a high charging cost to complete their trip. And when we search to minimize the charging cost of each vehicle type, we need 64 gates, which is a high number compared to the previous results. And we find that just 8 gates have a positive gain. In this case, each vehicle type uses the charging line when the load is needed, And due to heterogeneity of batteries, each vehicle type uses a set of gates to minimize its charging cost. For that, we found that 56 gates not profitable, and for the same cost, the number of open gates in the road increases. So our result demonstrates that our optimization goals are conflicting. That's meaning the improvement of the one objective comes at the expense of the another objective. Donc for that, the next step of our work is to find a compromise between the two objectives using a meta-heuristic method. And thank you for your attention.